I welcome you in this NPTEL online course on earthquake resistant design of foundations. And as we discussed in the first lecture that this course consists of 5 modules. The second module is on shallow foundations which we was discussing, and today we will continue with that. Among this second module on shallow foundations, as we have discussed that we have already discussed the general requirements, bearing capacity and settlement, combined footings, raft foundations, and in the last 2 lectures also we have discussed footings subjected to dynamic loads. However, when we discuss this, then we have considered that footings may be subjected to dynamic loads in 2 categories, and when we have the dynamic so these were the issues which were discussed for the footings which were subjected to dynamic loads. We have considered dynamic loads and methods of analysis, then pseudostatic analysis, earthquake loads for horizontal as well as moment was considered, then eccentric load on footing was considered. Finally, we have considered a new method for design of eccentrically loaded footings, where we have discussed bearing capacity as well as settlement. Then for the new method, design procedure as well as one design example was discussed, and finally we end up with inclined load on a footing. Today we are going to continue with that, with a difference that the foundations which are subjected to dynamic loads, as discussed earlier, it may be due to earthquake, blasting, operation of machine, or maybe wind loading also. So, there are 2 types of methods of analysis, one is pseudostatic analysis, another is dynamic analysis. Pseudostatic analysis has been already discussed in detail, and today in the next lecture we are going to talk about dynamic analysis, where you consider not only a static load, rather you consider transient excitation which may be simulated for earthquake loading. So, today and in the next lecture will be exclusively on dynamic analysis for foundations. So, when we have for the shallow foundations, first thing is that these all 3 methods which we are going to discuss for dynamic analysis are based on analytical approaches, and the common assumption is that the soil rupture under transient loads occurs along a static rupture surface. That means, rupture surface considered is static, that is not dynamic, that we consider a rupture surface, and along that rupture surface we will consider the transient loading applied. Under this dynamic analysis, we are going to talk about 3 methods. One is for transient vertical rotational loads, and that approach was given by Triandafilidis in 1965. The second one again for transient vertical load, but for reciprocating loads was given by Wallace in 1961. The last one is for horizontal reciprocating load, and that has been reported by Chumer in 1965. And then finally, after considering these 3 theories, we will discuss some numerical examples. So, let us talk first one, that is the Triandafilidis approach. So, when we talk about Triandafilidis solution, then there are certain assumptions under this. First of all, as said, this will be applicable for vertical loads and rotational loads, when we are considering the vertical load, but the load is rotational one. And the Triandafilidis study the responses of footings in saturated cohesive soils which are subjected to vertical dynamic load pulses of defined shape. That means first of all, that loading shape or loading excitation is already defined, and this will be applicable only for cohesive soils, not for cohesionless soils. That means, it may be for clay, not for the sands. The assumptions for this theory are listed here. First of all, the failure surface of soil is assumed cylindrical. The saturated cohesive soil behaves as a rigid plastic material, as shown in this figure. You could see in this figure that when we talk about stress strain relationship is, in this case you have a straight line. So, that means there there is no change in stress, but strain is continuously increasing. The forcing function is assumed to be an exponentially decaying function, which we are going to discuss later. The influence of strain rate on shear strength of the soil and the dead weight of the foundations are neglected. That means, what we say for this theory, you will assume that the behavior of the soil is not nonlinear, only the plastic behavior will be considered. The second thing, that this inertial force of the footing will be neglected. So, with these assumptions we continue with this solution. So, the Triandafilidis considered this solution decaying stress at time t, which is given by this relation, which is listed here, q d equal to q naught E minus beta t, where you have q naught is nothing but lambda q u E minus beta t. So, what you have q u is nothing but static bearing capacity of continuous footing, and lambda is overload factor, which can be simply lambda equal to q naught over q. That means, with respect to the q u, how many times you have this q naught. So, that is there, and then beta is decaying function. The transient load is shown in this, like you could see that this is shown here, where you have with the time it is varying, and you can see when t equal to 0, if I put t equal to 0, then naturally q d will be equal to q naught, okay. And it is continuously decaying function. That means, when the time is increasing, the value q d is exponentially decaying exponentially, and this is reducing, almost reaching to a negligible value with the time. So, this is the decaying functions which has been considered by Triandafilidis, and we continue with this approach. Now, as conveyed during the assumptions, that this theory, it is assumed that the failure surface is cylindrical. So, it is shown in this figure here. So, what you could see in this figure, that there is a cylindrical surface and the failure or rupture surface is shown solid line as well as dotted line. So, dotted line is for Prandtl rupture surface, while the solid semicircle is Fellaini rupture surface, and it is assumed that footing is kind of a surface footing. That means, embedded of the footing is not considered. The b is the width of the footing, and q u is the ultimate bearing capacity, which is shown here. So, what we have in this case, from this center point, the distance of the center of rotation is 0.43 b. However, when this is rotated by an angle theta, as shown in this figure. So, what will happen? It is like this, it will get rotated. So, naturally one part will go, and then, but still, as you know, that always the weight of the slice or weight of this vase will always act in the vertical direction w. So, this is weight is, even it is get tilted, but still its weight w will be acting. And if we resolve this w into two components, one is normal to this vase and another is perpendicular, one is normal and another is in this horizontal direction. So, you have w cos theta and w sin theta, they are nothing but components of this w in two directions. Now, there are two center, one is center of rotation as before, which is here at the same point, but under the slice also there is what is called center of gravity, where the weight is acting. The distance r naught, which is distance between CZ and center of rotation, is given by 2.205 b over pi. So, this is fixed in this case, where b is the this width as shown here, which is equal to the width of the footing, but b can be treated as here the radius of the cylindrical surface here or semicircle here. So, what with this geometrical explanation, now because this is a load applied is a dynamic load in the form of this which we have shown, the decaying function. What will happen with this load, that when this load is applied, this slice will get disturbed, and this get rotated with an angle theta. What will happen when we disturb this one? Then after this disturbance, you have equation of motion, because in the dynamics the next step is what is our objective is to frame an equation of motion, and we solve the equation of motion and then find our basic unknown. So, what is basic unknown in this problem is theta. So, theta is basic unknown and our objective is to get the value of theta. So, ultimately our objective will be that to find the value of theta in this problem, and for that we use what is called moment equilibrium, and moment equilibrium once we consider, then moment equilibrium will give you this equation of motion, and that will be a differential equation, solve that equation and find the value of theta. So, in this equation of motion, moment, what we do, moment of disturbing forces to moment of resisting forces, and that is done about point O. So, you have the point O, you could see the point O here, and so what you have, driving moment and versus applied dynamic pulse. So, in this case you could see here that driving moment is equal to applied dynamic pulse, where driving moment is coming due to your loading function which is QD, and QD multiplied by B will give you force, and that will be, of course, that will be per unit length, because QDB will be kind of a UDL. So, when you consider over the unit, so this will be the UDL, and due to this force the moment about the point, the moment is find out about this line. So, moment this will be acting and this moment is calculated about this point. So, this O, center of rotation. Then similarly, the static bearing capacity of continuous fluid along the failure surface will be Qu and which is 5.54 Cu. Actually, this is according to this Maheshwari NC, this is, so basically if I put this in, this can be put like this also, NC into Cu. So, basically where NC, Cu is underend shear strength and NC is considered in this case is 5.54 for saturated cohesive soils. So, with this Qu, the next step is this, due to this Qu, what is the moment created? So, moment created is will be this Qu will try to have resisting moment. So, what you have actually what will this Qd will try to create a driving moment, while this Qu will be acting this like this will be acting in this direction, while Qu will try to clockwise, anti-clockwise, and this first one will be acting clockwise. So, as a result the resisting moment is given by this relation 2b, which is given MRS half Qu b square, where b is the width of the footing. The resisting moment MRI due to the rigid body motion of the failed soil mass will be given by J naught theta double dot, where theta double dot is second derivative of theta and J naught is nothing but J naught is the polar mass moment of inertia, which given the width of the footing, this can be found out, J naught is found out from this equation, and once we put back this in this equation, then you get here, and the weight of the cylindrical soil mass W can also be found if you know the unit weight of the soil, and that can be calculated from this equation. So, this is resisting moment, and this resisting moment is due to the rigid body motion of the failed soil mass. Now, what we do ultimately, then the last one is the displaced position of the soil mass, which generate a resisting moment of MRW, and that means the component, this component W sin theta will also create a resisting moment, and because W sin theta, if you find its moment of about this point O, so it will be W sin theta into R naught only simply. So, what you have here W sin theta into R naught. So, we 2D equation 2D gives you this moment. Now, we combined all these 4 moments, where one side on the left hand side you have the driving moments and on right hand side you have the resisting forces or resisting moment. And once you put all these values here in this equation, you could see that and then you solve this equation, that means in terms of Qd and taking Qd and Qu one side, and then finally you end up in equation number 4. So, equation number 4 is called the equation of motion, and you can see that this equation is second derivative, that means because theta double dot here is nothing but theta double dot is d square theta dt square. So, now the next stage is to solve this equation of motion to get the value of theta, and that is our unknown, and naturally we will be, as an engineer, we will be interested in the maximum value of theta, that is theta max, for the design purpose. So, what has been done later by Triandafilidis, that they have solved this equation, first of all equation 4, and find the natural frequency, which can be simply find out. Suppose this is mx, this can be compared, this relation can be compared with the mx double dot plus kx equal to forcing function. You have this some forcing function. So, omega n in this equation is given by k by m. So, you have this one. So, the k is 3g by pi by b and m is 1. So, the root of that. So, omega n you can be find out from the equation 5a. That means, the natural frequency for this case will exclusively depends only on the width of the footing and the value of g, which is constant for the that is the acceleration due to gravitational acceleration. Period can be find out from equation 5b, where t capital T is nothing but 1 over f, that means 2 pi over omega n, and that can be calculated from equation 5b. So, rearranging equation 4, one can have this equation, and then again then what we have, that maximum value of a factor where dimensionless factor, which is k w by 0.68 g q mu theta max, and in terms of sorry, this is not dimensionless in second square. So, this is this factor is called k. Actually here what is done, that this theta max is normalized. So, to have a dynamic load factor, and what the Triandafilidis have proposed, he has given the charts to have the value of k for different width of the footing. He have considered 3 width of the footing, b equal to 0.6 meter, 1.5 meter and 3 meter. So, one of the case where b equal to 0.6 meter is shown in this figure. So, you could see that here b equal to 0.6 meter, and in this chart when we have for b equal to 0.6 meter, similar chart has been given when b is varying 1.5 meter and 3 meter. What has been shown in this chart, on the x axis you have the overload ratio lambda, which is varying 1 to 5, because its minimum value is 1 and 5 is quite high value. And then on y axis you have this factor k, which can which is in terms of second square, which is given here, and you can observe that both x axis as well as y axis both are on the log scale, they are not normal scales. So, you have this one. When the b equal for 0.6 meter, the decaying function beta is varying, and you have the values 0, 0.5, 1, 2, 5, 10 and 50. Now, the issue is this, how to use this chart for the design purpose. What do you need to do for the design purpose? First, this chart will be applicable only when you have b equal to 0.6 meter. So, if width of the footing is 0.6 meter, then we can get the value of beta decaying function. Then according to you select a curve, overload ratio, for given value of overload ratio and beta, you can find the value of k from this chart, and once k is known, then using this equation you can find the value of theta max, and once we solve the one numerical example, then everything will be clear. It is possible that suppose if you do not have this chart, then how you can design? Then naturally you can directly use this equation, equation number 4, to this equation number 4 for finding the theta value or theta max value, solving this theta here. Now, this was regarding the Triandafilidis solution. The next one, the second one, that is called Wallace solutions, and both Triandafilidis and Wallace solutions are applicable when the load is applied vertically, that transient load is applying. But the first one was applicable when you have the load is rotational, and in this case Wallace have considered, instead of rotational load, they have considered the reciprocating load or vertical load. And another difference, that Triandafilidis case was applicable for saturated cohesive soils, but Wallace solution is applicable for C5 soil. So, that means there is no restriction, that here C5 soil is considered, and as we discussed earlier, that this is applicable for vertical loads. So, let us discuss that what are the procedure suggested by the Wallace for this, and what was the assumption first. So, what is the assumption? The first assumption is here, the failure surface in the soil mass is assumed to be similar as suggested by Tarjagi in 1943 for the evaluation of static bearing capacity of strep footings. So, one thing is that it is assumed that your footing is strip footing, and This is shown in the figure here. What you have in this figure? B is the width of the footing and df is the depth of the footing. Here df, depth of the footing is also considered, B is also considered. In the earlier solution the footing was considered on the surface, but here the footing is embedded and its depth is df. Then phi is the angle of internal friction and the ultimate shear strength is given by tau equal to C plus sigma tan phi, which is very famous Mohr Coulomb's equation. And the second assumption in this theory that the soil behaves as a rigid plastic material is similar to what we have considered for the earlier theory, that is Triandafilidis theory. So, this is the same, that means it is considered to be plastic material. Now, the dynamic load which is applied to the footing is also decaying function, initially peak triangular force pulse, which is we will discuss later. So, again with the time the force is decreasing here and the footing is assumed to be weightless and to impart uniform load to the soil surface. So, this is also similar assumption which we have considered. So, in this case the failure surface is similar to Tarjagi. So, it is very practical and the load I have considered is also vertical. Of course, vertical load will be always there even if you do not apply the dynamic load, but what we are considering the vertical load is reciprocating, that means it is tangent loading is or the load which is varying with the time is considered in this analysis. So, what you have now here that first of all in the Wallace solution the loading function is shown here, that is loading intensity, that it is peak value here, this is the peak value, and as the time increases that it will decrease and after at time Td the load becomes 0. So, that means this loading function can be shown like this. When you have time between T to Td, the time is in this range, that loading function can be simply represented by Qb 1 minus Td, but if T is more than Td then naturally loading function is 0. So, in Tarjagi's failure surface BD is an arc of logarithmic spiral with its center at O. So, what is here? What you have, if I see in this case, so you have both sides, if I put a straight line here, you know that, so there is a mirror image on the left hand side and the right hand side you have the both the sides same thing. Let us see on the right hand side what you have on the right hand side. You have point A which is the edge of the footing, then point B which is the center of this triangle, and then C and D. Between B and D this is what you have the logarithmic spiral. The point D can be located simply by matching if you have draw a line at an angle 45 degree minus phi by 2 from point A, then you can draw the have the point D and B to D is a logarithmic spiral. Now, what you have in this case, R equal to R naught E theta tan phi, where R naught is nothing but your OB. So, you have this R naught and theta will be this angle which will be varying according to. So, as the theta varies naturally R will be changing for given value of R naught. So, as this R naught increases this theta increases, R naught this R will be changing here in this case. Now, what you have, so this is this BD for the logarithmic spiral at center O, as just we have discussed. R naught is distance OB and phi is angle of internal friction of the soil. Now, the static bearing capacity Qu for this failure surface is given by this relation C n C plus gamma df nq plus 0.5 gamma b n gamma. So, this is a very famous equation of Tarjagi's theory. So, nothing new in this, but what is done by this researcher Wallace, in addition to the Qu, they have also considered the inertial force which is given by If, which is given n I gamma b squared d squared delta dt square. What is delta here? Which is delta is displacement at any time t, and this is your basic unknown in this theory. So, our ultimate objective is to get the value of delta by the analysis. What is Ni? Ni is called coefficient of dynamic initial shear resistance, and this is a dimensionless quantity. The coefficient of Ni also depends on phi and a factor k. What is k in this case? K is a new capital K is a new introduced parameter which is simply 2 times of OAB, where OA you can see in the like this here, O is this point, right, and A is this point. Now, O is the center of rotation for this logarithmic spiral, and how we can locate, if we know the value of R naught decided, then B is already known. So, if I draw a line from B to O that this distance is R naught, then you can locate this one, or like you can find the center of rotation for this logarithmic spiral. So, for this logarithmic spiral, O is the center of rotation, R naught is the radius, and phi theta is angle which is varying here. So, OA is shown in this figure, and this K can be written as, basically this can be written in another form. This is OA divided by B by 2, where B by 2 is nothing but half of this width of the footing, that means this distance here. So, this is a ratio, naturally K will be dimensionless, there will be no value of this. So, the Ni depends on phi and K. Then moment due to displacement is given by this relation, where you have this NRB gamma delta. So, this in fact this will be a force. So, this will be the force due to displacement, not due to moment, sorry about this, the force due to displacement, and then you can have this, you can find using this equation. In this equation, NR is coefficient, which is dimension in meter per second square, and this also depends on phi and K. So, now we have for this Wallace solution 5 parameters. One is NC, NQ and N gamma, which are similar to Tarjagi's theory, but there is a one basic difference between Tarjagi and this theory, that NC, NQ and N gamma are not only dependent on phi, but in this case they depends on the factor K also. Okay. Then 2 more parameters has been introduced, which is one is Ni, another is Nr, and both these 2 parameters also depends on phi and K. So, after the analysis, Wallace have given a table where you can find the value of these 5 parameter NC, NQ, N gamma, Nr, Ni. This table is shown here typically. In this table, let us analysis. What you have, first column is for phi, and these tables are given for phi equal to 0, then phi equal to 5 degree, 10 degree, 15 up to phi equal to 40 degree. Then the value of K are varying, like for when 0, then 3 values are there, minus 0.05, 0 and plus 0.05. For other values, they are varying from minus 0.65 to plus 0.05, and for a given set of phi and K, 5 parameters N gamma, NC, NQ, Ni, Nr has been given in this table. The last column root Nr over Ni can also be found simply this using column 6 and 7 of this table. So, the last column is basically can be found from other 2 columns. So, it is extra. What you can have, basically what you find from this table, that for given value of phi you have the 5 coefficients, 3 bearing capacity parameters and then another inertial and resistance force. So, this is use how this. Now, the issue is this one, this table is there and the values are known, then how to use it. So, what is done, basically again the same treatment is done, that we use the equation of set up an equation of motion, and once an equation of motion is known to you, then solve that equation of motion and find the value of delta. So, what you have, the differential equations are set up by equating the 4 vertical forces to 0, and this must be separated for when time 0 to Td and when time t is more than Td. So, what you can have, for the first case, when your time t is less than Td, then the equation of motion is set up like here, and what you have on the left hand side, there is delta, the derivatives of delta, while on the right hand side you have values which are already known to you. So, what we do, using both these equations, we solve these equations and find the value of delta. The solution of these differential equation will can be represented by this is the case, and this will be the case for when you have time less than Td, and this will be the case when t is greater than Td. Okay. So, And once we there are 4 constants in these equations C1, C2, C3 and C4, and then another parameter k prime is introduced here, which is ratio of 2 NR or NIB, because NR is known, NI is known, B width of the footing is known. So, naturally this parameter k prime can be calculated, but mind it that the value of k prime is not dimensionless, rather than it have the unit inverse of the time, that is second inverse. So, once we multiply this with the time, then this will give you the radian, or this you have the degrees in the form. So, C1, C2, C3 and C4 are coefficient of integration, and these coefficients can be find out simply by applying the boundary condition. First, C1 and C2 can be obtained by the initial boundary conditions, while C3 and C4 can be obtained by applying the boundary condition at time t equal to Td. And after that we can, once we find the C1, C2, C3, C4, that means your equations are ready, and then last item is that to get the value of delta max, and delta max is nothing but the maximum value of delta. So, maximum value of delta is find out, and this delta max can be determined from the chart which has been given by the Wallace. And let us see this chart, and in this chart what you have, you could see on y axis as well as x axis, both axes first of all in the logarithmic scale. Okay. Y axis is nothing but Td into k, actually this is Td into k prime as shown here. So, this will be a dimensionless number, and Td into k prime, because k is known to us, Td the duration of the pulse which you are applying is also known. So, Td k, this product is known, so that means y axis is known. Then what we do, we find the value of q by qu for the given load. Qu is the ultimate bearing capacity, q is can be find out from the given load, and then this ratio, there are curves which are varying from 1.10 to 3. So, in these curves what you have, you select a curve which is applicable for your case, and out of these curves, once you pick up that curve, using that curve finally for a given value y axis drop and get the value on x axis. X axis is nothing but gamma nr Qu over delta max, and once this factor is known, then because gamma is known, nr is known, Q is known, so then you can find the value of delta max. So, this way the maximum value of delta max can be find out, which is our basic objective. So, I conclude today's presentation and this discussed lecture by saying that we have discussed 2 theories today. One is Triandafilidis and another is Wallace solution. Both the approaches are applicable for vertical load, but first one is applicable for rotational mode, second one is applicable for Wallace solution. Again, that first solution is applicable for saturated cohesive soils, that is when phi equal to 0, while the second solution is applicable for C phi soil. But both these approaches were applicable only for vertical load, but when an earthquake comes, it is not only vertical load, but horizontal load is also applied. And how to deal with the case when an horizontal load is applied, we are going to discuss, that is in the next lecture, and that is basically tumor solution. And in the next lecture we are going to discuss tumor solution as well as some numerical examples also. So, with this I thank you very much for your kind attention and see you. Thanks.